take a rectangular hyperbola H and let O be its center. Now let's choose a point Q anywhere on said hyperbola H. Okay? I'm now going to draw a circle K centered on this chosen point Q, passing through the center of the hyperbola O. Okay? Very simple construction. Rectangular hyperbola, O is its center. I'm going to choose a point Q anywhere on it, and I'm going to draw the circle centered on this chosen point Q, passing through O. It turns out, and Professor Ronaldo Garcia discovered this, that the pair H, K admits a Poncelet family of triangles. One of these triangles is an equilateral. Okay? And surprisingly, if you interchange their roles, meaning let K be the incidence Poncelet conic and let H become the tangency one, this pair can be reversed in such a way that K and H will also admit a family of green triangles inscribed in K and circumscribing the rectangular hyperbola. What's really surprising is that this works for any Q on H. So if I put K over here, Q over here, it's a different point, right? I continue to have bidirectional Poncelet. So you have this family of blue triangles, and you have a family of green triangles in the reverse order. So we thought this was quite cute, and we're working on the theoretical reasons for it. Another thing that you can investigate here is you can show the locus of, for example, the orthocenter, sorry, the barycenter x equals to x2 of the two families. So this first family here, the green family, seems to be describing an arc of a circle, while the other family, the blue one, seems to be describing something that looks like a conic in this phase, and then there's an inverted phase of this triangle, which is over here, where x2 sweeps what looks like a straight line. So you have an inverted phase of this blue triangle, as well as an encompassing or sort of more non-inverted version of this family. If we go to x3, the circumcenter, we also find an interesting phenomenon that the circumcenter of the blue triangles follow a straight line that goes through Q and it's tangent to the hyperbola H at Q. Okay? Obviously, the circumcenter of the other family is stationary at the center of K. But what's interesting is when x3 of the blue reaches the center of K, you get to the position where the triangle is equilateral. Okay, so this family does contain an equilateral triangle. The orthocenters of the green family looks like the arc of a circle that goes through O. Okay, we saw in a recent publication that the locus of the orthocenter is always homothetic to the incidence conic. So if this is a circle, we expect this guy to be also an arc of a circle. Now, interestingly, for the blue family, the locus of the orthocenter is the hyperbola itself, is H itself. So that's quite interesting. This is an interesting family, right? This blue family. Let me show one more locus of interest, that of x5. Okay, so x5 is the Euler center, the center of the 9-point circle. This is also on a line, and it has these two extrema. It has an extremum at Q when the triangle is equilateral, and then it sort of goes through infinity and comes back at the averted state at this other side here of, and I don't have enough precision here. Yeah, I do have some precision here, but it comes on that other side, on the averted side, on a straight line. And then it comes back through infinity to the non-inverted configuration back to Q, all the way to the equilateral situation. Oh yeah, one more, the Feuerbach point. The Feuerbach point, let's go there, x11 over here, is stationary. over the family while in the non-everted state. When it goes everted, X11 has a different path that is not being shown here for some reason. There could be some instability. Let's see, if I move Q a little bit, I might show that locus. There's some instability in the locus calculation in GeoGebra, but it doesn't matter. It's actually doing something not that interesting up there, but what's interesting is when you're in this non-everted state, X11 is stationary. All right, thank you for watching. See you on the next video.